Welcome to this explainer. Let's dive right in and transform your base knowledge of why files are needed for persistent storage into absolutely gold standard, top-scoring Cambridge exam answers. Think of this as your alchemy class for computer science. I am going to show you exactly how to take the raw, basic materials of computer science facts that you've memorized and transmute them into the precise, evaluative language that Cambridge examiners are actively hunting for. Now, while our primary focus today is on the 9618 A-level syllabus, the analytical depth and the exam techniques we are going to cover apply across the entire Cambridge spectrum. Whether you are sitting for syllabus codes 0417, 0478, 0983, 0984, or 2210, this methodology is your key to unlocking top marks. If you have ever walked out of an exam hall feeling absolutely fantastic, thinking you totally nailed the paper, only to get your results back covered in red ink, then listen up, because this explainer is designed specifically for you. We're going to completely deconstruct the exact answering methodology that separates your average middle-of-the-pack candidates from the absolute top percentile of students. We're looking at real past paper scenarios, real examiner reports, and building a strategy that works every single time.
Now, you might be wondering, why are we focusing so heavily on persistent storage? Well, look at this. The stakes here are absolutely massive. Our analysis of past papers reveals that this single overarching topic, data storage, file handling, and the algorithms surrounding them, can account for up to 15% of the total marks in your Paper 2 exam. Think about that for a second. 15%. That is not just a handful of bonus points. That is quite literally the entire mathematical gap between two full grade boundaries. It is the difference between an A and a B, or a B and a C. When we talk about Section 10.3 of the syllabus, which covers files and why they are needed for persistent storage, students consistently brush past it. They think, well, I know what a file is. I save my documents every single day on my laptop. How hard can this be? But the Cambridge assessment objectives demand so much more than mere recognition or basic user-level understanding. They demand a complete mastery of fundamental principles, highly systematic analysis, and rigorous evidence-based reasoning. If you leave these marks on the table because you think the topic is too basic to revise deeply, you are making a critical structural error in your exam strategy before you even pick up your pen in the exam hall.
So, this completely begs the question, why do candidates struggle so much with files and persistent storage when the basic concepts seem so incredibly simple? It really comes down to how Cambridge examiners actually assess your methodology, not just your factual recall. To understand this, let's look at two very typical student profiles that we see constantly in past paper data. First, we have Alex. Now, Alex is a walking textbook. He overloads his exam answers with raw computer science facts. If you ask him about persistent storage, he will write an entire massive paragraph defining a text file, a binary file, how a magnetic hard drive platter spins, and what a solid-state drive is. But he includes absolutely zero critical analysis. He doesn't actually answer the specific prompt on the page. As a result, the examiner's red pen just slashes right through his massive block of text because he hasn't hit a single assessment objective. Then, on the other end of the spectrum, we have Sam. Sam rushes. He completely misses the command word requirements. If the exam question explicitly says, evaluate the need for persistent storage, Sam just describes what a file is. He'll write, file save data so it isn't lost, and think he's done. Both Alex and Sam know exactly what a file is, but when we put their answers side by side, we see they are fundamentally flawed. Why? Because they entirely lack the required structural framework to capture the marks.
So the crucial point we need to get across here is that understanding persistent storage isn't just about knowing that a file lives on a hard drive. It requires deep, demonstrable causal relationships and true analytical depth. You literally cannot just say files are kept on a disk. You need to demonstrate a complete conceptual framework to the examiner. You must articulate the theoretical architecture of what persistent storage actually achieves in a computing system. For example, why does the state of a specific application need to be maintained? Exactly what happens at the hardware level during a power cycle? How does the active data structure sitting in volatile memory translate seamlessly into a binary representation on a persistent drive? This is where you have to break down those command words we talked about earlier. If the command word is explain, you need to provide the how and the why. If it's evaluate, you must provide advantages, disadvantages, and a justified conclusion. The Cambridge assessment framework prioritizes analytical depth over superficial breadth every single time. Answering a question on this topic means proving you understand the underlying logical reasoning, not just reciting a glossary definition you memorized the night before. Before we continue, subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. And this right here brilliantly illustrates the principal examiner's mindset. This is a direct quote from the examiner reports. You absolutely must demonstrate connected conceptual understanding that transfers to entirely unfamiliar contexts. This is the secret to scoring the top bands. And this is exactly where we introduce our core strategy, the PEAL framework. That stands for point, evidence, explanation, link. Top-tier computer science students structure their answers deliberately. First, they make a clear point about persistent storage. Next, they provide evidence directly from the scenario provided in the exam question. Then they provide a technical explanation of the mechanism. And finally, crucially, they link it to cross-topic connections. These connections are your absolute secret weapon. If you can take a question about file handling and seamlessly link it to binary data representation, or operating system resource management, or the time complexity and efficiency of an algorithm, you instantly elevate your answer from completely average to incredibly exceptional. You are showing the examiner that you don't just see the syllabus as separate, isolated chapters, but as one unified computing system.
Let's move along and see how this PEAL framework builds directly into what we call the procedural pipeline. This is a standardized, repeatable sequence that basically guarantees your systematic processing is exactly what the graders are looking for. It is the ultimate transformation for your exam technique. Whenever you faced a 9618 procedural question on files, you must follow these 5 steps rigidly. First, identify the key elements from the prompt, exactly what data is volatile right now and desperately needs persisting. Second, apply the relevant principles. Are we going to use sequential access or random access for this specific file and why? Third, execute your analysis with completely clear working. Fourth, verify your results against the specific constraints of the scenario given to you. And finally, present it in the exact format requested by the command word. This pipeline is not just a helpful suggestion. This is the literal rubric that Cambridge examiners use to award marks. If you skip a step in your written explanation or in your pseudocode logic, you will drop the mark. It is that simple.
Never, ever forget the method mark strategy. Examiners explicitly warn year after year that students lose massive amounts of points simply by not showing their working. So you need to secure those process marks every single time. This is an absolute examiner alert, guys. I really cannot stress this enough. When you are writing an algorithm to read from or write to a persistent file, or when you are mathematically calculating the storage requirements for a database, you must show your logical steps on the page. If you make a minor arithmetic error or a tiny pseudocode syntax slip, but your entire deconstruct, solve, evaluate process is clearly visible on the page, the examiner will enthusiastically award you method marks. They want to give you points. But if you do all the math in your head and just write down a final flawed answer, you get a 0. Nothing. The transformation from a paper covered in red ink to one full of green check marks starts with making your completely invisible thinking entirely visible on the exam paper. When dealing with the practical programming side of persistent storage, your algorithmic thinking really has to follow these 4 specific steps to effectively manipulate data from its binary representations. Step 1 is step-by-step decomposition. You have to break the file handling task into its core components: opening the file, reading the stream, processing the data, writing it back, and safely closing the file to prevent corruption. Step 2 is appropriate data structure selection. Are you pulling this file data into an array, a 1D or 2D array, a record, a linked list? You must explicitly justify why that structure fits the scenario. Step 3 is efficient code implementation. You need to ensure your while loops reading the file don't cause buffer overflows or infinite loops. And step 4 is rigorous testing logic. How does your algorithm actually behave if the file doesn't exist in the directory? What happens if the file is completely empty? Remember our students Alex and Sam from earlier? When Sam rewrites his previously rushed answer using this exact 4-step framework, explicitly addressing those file edge cases, his marks instantly transform. Showing the examiner you have proactively thought about these precise technical details is exactly how you capture the highest possible grade.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's jump right into our interactive workshop segment. To hit those really difficult, higher-order assessment objectives, you need to engage in pure evaluative thinking. You have to deconstruct the problem, solve it, and evaluate it by deeply analyzing trade-offs and acknowledging the limitations of your own solutions. This is the absolute hallmark of top-scoring candidates. Let's do a quick data scan challenge. Imagine you are presented with a complex data table showing the speed, cost, and volatility of various storage mediums. When the exam asks why files are needed in this system, you don't just give one basic reason. You evaluate. You consider multiple solutions. You actively analyze the severe trade-offs between storing the application's active data in highly volatile, expensive RAM versus pushing it to persistent, cheaper secondary storage. You openly acknowledge the limitations, like the significantly slower read and write latency of persistent storage compared to primary memory. And most importantly, you justify all of your architectural design decisions with hard numerical evidence derived directly from the exam question's specific context.
Let's compare a fundamentally basic answer to a high-scoring one. You can't just list facts. You absolutely must use comparative connectives to show both similarities and differences, all backed by hard evidence. Let's play a quick game of Find the Flaw. I'm going to give you a flawed computer science paragraph, and I want you to mentally identify why it loses marks. Ready? Here it is. RAM is really fast. Hard drives are much slower. Files save data so it doesn't get lost. Did you spot the flaw? It is just vague listing. The examiner gives that 0 marks for evaluation. The assessment framework rigorously demands comparative analysis. You need to identify the similarities and the differences in the same breath. You must force yourself to use comparative connectives like whereas, conversely, in contrast, or on the other hand. Let's fix that flawed paragraph. A gold standard answer sounds like this. While RAM provides rapid access times necessary for active CPU processing, it is inherently volatile. Conversely, files written to persistent storage ensure critical state retention across power cycles, albeit with a trade-off of higher access latency. Do you see the huge difference there? That is a perfect PL paragraph in action.
Here is a full autopsy of the top 3 mistakes pulled directly from the principal examiner reports, showing you exactly how to correct vague, context-blind answers into precise technical details. Let's look at examiner warning number 1, vague answers. The guaranteed fix here is specific technical details. Don't ever just write, "the program breaks." You need to say it results in an unexpected end-of-file reading error causing a runtime crash. Warning number 2 is ignoring edge cases. When you design an algorithm for persistent storage, you must check boundary conditions thoroughly. You have to ask yourself, what happens at the exact boundary of the file size limit? What if the storage disk is completely full when the write operation is called? Warning number 3 is relying on generic responses. If the exam question is explicitly about a hospital database system, your answer about persistent storage must specifically mention saving patient medical records, appointment times, or doctor schedules. You cannot just use the generic word data. You must lock your answer tightly to the provided context, or you will drop the application marks. Look at this incredible alchemical transformation in practice. The incredibly vague answer on the left fails completely, while the specific, context-driven answer on the right captures maximum marks. This brings us to our speed writing challenge. Imagine you are in the exam hall, the clock is ticking, and you only have 30 seconds left to write your final sentence. You have to make it count. Writing files save data is a 0-mark placeholder. It shows absolutely no analytical depth and proves nothing to the examiner. But look at the gold standard on the right. Persistent storage prevents volatile data loss during power cycles, maintaining state for the specific application context. That is a masterpiece of a sentence. In just one single sentence, you have successfully demonstrated a deep grasp of memory volatility, hardware power states, and application relevance. You have extracted the core trend of the entire syllabus module and presented it perfectly in seconds. This is the real difference between just writing words to fill space on the page and writing strategically to score top marks. To wrap up our analysis today, this right here is your ultimate blueprint for mastering persistent storage. Connect the topics, explicitly show your process, get hyper-specific, test those boundaries, and always stay in context. This cheat sheet represents our final system for absolute exam mastery. If you want to see your progress bar shoot to 100%, you need to remember the 3 overarching rules that guarantee top marks. Number 1, command word decoding. Know exactly what evaluate or explain requires. Number 2, applying the Peel framework for every long-form answer. And number 3, using a time management matrix so you don't rush like Sam did. When you turn the page and see a heavily weighted question on 10.3 files, you execute this blueprint immediately. You integrate your knowledge of data structures, you show every single line of your algorithmic working to ruthlessly exploit the method mark strategy. You drill down into specific technical terminology, you actively hunt down those edge cases, and you absolutely refuse to write a generic, context-free answer. As you prepare for your actual exam, I want you to think deeply about this final question on the screen. Consider exactly how you will deconstruct your very next practice problem to ensure that absolutely no marks are ever left on the table again. Take this blueprint we've discussed today, apply it rigorously to your next past paper, and watch how it transforms your understanding into top-tier, gold-standard results. Keep evaluating, keep analyzing, and keep refining your technique. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGSCE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGSCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.